Great news! We finally have a formula to calculate rates of change, tangent lines to curves at any point. If you don't know how we obtained it, you should probably watch the video and check the lecture notes on section 4. We finally defined what a derivative is from first principles. The process is called differentiation, and the derivative of a function f and Newton's notation can be written like this, or with a dot on top. It means the same thing. In Leibniz notation, we use dy, dx, and as we've seen from geometrical arguments and making secant tend to a tangent, this can be obtained by calculating the limit when dx goes to 0 of fx plus dx minus f of x over dx. And it is important to note that we're calculating this limit. Right? So we're applying the limit operator in calculating this. It also means that all the knowledge from section 3 about limits, how to calculate them, and going through the lists is crucial actually to obtain derivatives from first principles. It's also important to point out that sometimes there is a more compact notation to this, because this quantity doesn't have to be dx, it could be anything. And it's quite popular actually to use a quantity h. So you will see in books and also in the lecture notes, I'll try to alternate. It's okay to use either as long as you are consistent within a problem or solution. This is the same as saying you're calculating the limit when h goes to 0 of fx plus this quantity h minus f of x over h. This can be quite convenient because in the processes of long derivations you will have to write these terms a lot, and this saves you essentially 50% of the time. It's just one character. The big question, of course, is how do we use these expressions in practice? It's of course all about calculating limits, but sometimes it's a bit confusing because we're not really looking at the function, and these expressions are still very general. So there's nothing like a concrete specific example to start off with, which we will do in the next video.